Okay, now same situation. Suppose we're going from walking from Thorn to Searles, but instead of having specific data like taking readings, suppose we had some sort of we actually had a formula that would tell us the velocity at any given time. So suppose here that v is actually, it's a function of time, really. It's like we can write f of t, and let me actually just give you a function. Say we use 60 plus 80t. So again, we could consider that to be, I mean, it's kind of contrived. I'm not going to lie. So you'd have t is time in minutes. And v is velocity in feet per minute. And yeah, it's kind of contrived because how would you ever how would I ever walk at a very specific, such a specific pace? But you can imagine trying to program a robot or something and say, okay, I want it to accelerate uniform, like at a constant acceleration, and so it's going to get faster and faster, and it's accelerating constantly. Then its velocity, its speed is going to go up at a constant rate, right? So that's sort of the sort of situation you could have here. And again, if it takes 5 minutes to go from Thorn to Searles, then how far is the distance? So let me draw this again. So let's actually think about, instead of drawing points, now we'll have an actual function, right? So let's put time, and on the horizontal axis, velocity on the vertical axis. Now we have something like, we know it's at 60 when time is 0, and when time is 5, it's going to go up to, if we plug in 5 for t right here, we're going to get 5 times 80 is 400, 460. So we're going to have height 460 here, and it's about like that. And then we're actually going to have a straight line connecting those 2 points, right? It's close enough to going through there. Okay, and so this is the graph of velocity. This is this is this graph. This is graphing this function right here, right? And so how could we now use this to estimate the distance? Well, a couple things. We could still do the Riemann sum thing to estimate. So we can still use, sorry about that. We can still use rectangle sums. Rectangle, can't spell rectangle. Which are these called? These Riemann sums. Sums to approximate the distance. Oh man, why is my... let's just say we wanted to do this with 4 rectangles. I mean, the examples we've done have been sort of nice, right? Like 5 minutes broken up into 5 intervals. What if we wanted to do 4 intervals? So let's try n equals 4. And so what is the delta t? What is the time interval length in this case? Well, let's think about this. So we want to break this up into 4 equal intervals. So maybe something like that. Right, well, how long is each one then? Well, let's see. So if we take 5 minutes to break up into 4 equal intervals, so delta t, we can actually write that down. There's actually a nice function here, or a nice way to compute it. If you just think about it, it's 5 over 4. One way you can think is 5 minus 0, because that's the width of the interval, over 4. So that's 1.25 or 5/4 minutes. And so then, right, and so then we could have 4 rectangles. What I really need to do is think about the 4 points on the graph that are above these. And so these, let me zoom in on this a little bit. This is time 1.25. This is time 2.5, 3.75, and 5, right? And you could plug those into this function and see that like this height, for example, if you plug in 1.25 into this, right, into for t right here, you actually get 160. So that is height 160. This is height 260. Actually, the numbers work out kind of nicely because of the way it's basically, you're going from 60 to 460 in 4 steps. So really it's just going up by 100. Okay, so say we wanted to do, I don't know, the right sum. Let's try the right sum. So, well, we don't know what this looks like now. We can sort of think of it as, okay, in the first minute, you're going to assume you're going 160 feet per minute. And so you get this, sorry, the first 1.25 minutes, the first minute and a quarter, you're going to go 160 feet per minute. And so you're going to get the area of that rectangle. And then the second minute and a half, second time interval, third time interval, and then the fourth time interval. Like that, right? Maybe I should make all these points kind of clear. Okay, and so in this case, what is the approximate distance? So I'm just going to start using this term Riemann sum more and more because it's kind of what this is called. So the right Riemann sum with n equals 4 is, well, what do? We get 160, that's really feet per minute, times 1.25 minutes, plus 260. Man, why is my Apple Pencil is acting up? Sorry about this. 260 times 1.25 minutes plus 360. So notice it's the same delta t each time, but the heights of the rectangles are changing, right? So I don't really care what that equals. You know, we could work out what that equals, but I really just wanted to say like this is what you would get. All right, and that would be an approximation. It would be an overestimate, right? Because these rectangles go over the graph. And we know now that the actual area is the exact, the actual distance is the exact area under the graph. So this is an overestimate. Now, but okay, so that's an estimate. But what I'll say is in this situation, so if we had a more complicated function, this might be the best you can do. But this is actually, we know that the area is the exact distance, right? So in fact, let me just try to draw on this picture. We know that this area right here is really what we're trying to compute, right? And if you think about it, because it's just all has straight line sides, we can actually break this up into what, a rectangle and a triangle, right? I mean, it's a trapezoid officially, but I don't want you to have to remember a formula for a trapezoid. So let's just think about this. We have this sort of picture right here. Let me just draw it. We have something like this. And we can say, well, that's really this rectangle plus this triangle. And let's see, the base of this rectangle and this triangle are both 5. So I'm basically doing, right, I'm breaking up into that. And what's the height of this rectangle? Well, it's this rectangle right here. So the height's clearly 60. So that's height 60. And then what's the height of the triangle? It's this triangle right here. And it's really it's really, it's sort of the height. The height is right there, actually, right? It's It's right there, which is 460 minus 60. It's height 400. So this is height 400. And so the area, so the distance equals the area. And the area of the rectangle is 300. And the area of the triangle is 1/2 times 400 times 5, which is actually 2,000, half of 2,000, which is 1,000. So this is actually 1,300 feet. So if we programmed a robot or something to move at this very precise speed, we could actually claim, and we knew it took exactly 5 minutes to go from Thorn to Searles, we could say, okay, it's actually exactly 1,300 feet. So this is an exact answer. And so certainly for like a linear function where it's just a straight line, you can find an exact answer, exact area underneath pretty easily. The issue will be what happens when we have curvy functions and how do we find the exact area underneath that. And that's where we go towards the fundamental theorem of calculus. But I'll still give one more, there's one more subtlety wrinkle that I want to talk about. So I will do that in the next video.